All right, our next unit is exponential and logarithmic functions. Our first section within this unit is rational exponents, which is allowing us the ability to combine radicals and exponents. The whole unit that we had earlier this year that dealt with radicals and simplifying radicals, there's a way for us to convert a radical expression into an exponential expression and then simplify using the exponent rules that we know from the past, which tends to be a little bit easier for some people, and they prefer to use that as opposed to the radicals, to just simplifying it as a radical. So let me go through this with you and show you how it can be easier, possibly just by using exponents. First thing we're going to do is just go over the exponent rules that we know from the past. First one being that if you have like bases that you are multiplying together, so you have b to some m power times b to some n power, all you simply do is add those exponents. When you are raising a power to a power, b to the m raised to the nth power, in that case, you multiply those exponents. When you are dividing like bases, you subtract the exponents. When you have a product all being raised to a power, you can just simply distribute that power to both of those bases. Similarly, if you have a quotient raised to a power, you also can just distribute that power to both the numerator and the denominator. And then last, just remember that anything raised to the 0 power is just 1. Okay? So knowing that from my exponent rules, we're now going to attempt to combine the exponents and radicals together. Before that, what I need you to be able to do is recognize when you see a base that is not one of these numbers here, 2, 3, 5, 6, 7, or 10. We need to be able to identify, can we break whatever number we're looking at down as a power of a smaller number? So what I mean by that, if I just think of the powers of 2, 2 to the first is 2, 2 to the second is 4, 8, 16, 32, 64, 128, 256. That's as high as I'll go. So that's 2 to the first, 2 to the second, 2 to the third, fourth, fifth, sixth, seventh, 2 to the 8th power. So what I mean by recognizing powers, if I see the number 32, you should be able to identify that that is 2 to the 1, 2, 3, 4, 5th power. If I see the number 128, that's 2 to the 1, 2, 3, 4, 5, 6, 7th power. I want to be able to do that for all powers of 2. All powers of 3, all powers of 5, all powers of 6, all powers of 7, and powers of 10. Now notice for 5, 6, 7, and 10, I didn't go very high. I only need the 5 to the 4th power, and then for 6, 7, and 10, you would just go up to the 3rd power of each. Also notice I didn't put the number 4 in here. I didn't put the number 8 or the number 9 in here, because if you'll notice, 4 is already a power of 2. 8 is also a power of 2, and 9 is a power of 3. So when I'm breaking powers down, I want to break them completely down, as far down as I possibly can, to one of these numbers here, 2, 3, 5, 6, 7, or 10. Okay? So, rational exponent. For example, if I have 3 raised to the 1/2 and then squared, just using my laws of exponents, I know when I raise power to a power, I multiply exponents. That's going to give me 3 to the 1/2 times 2, which is 3 to the 1st power, which gives me, right? So now, normally in class, I would have you go through and come up with this for me, but basically what I would ask is, if 3 to the 1/2 squared equals 3, we can then deduce from that that 3 to the 1/2 must equal the square root of 3. Because again, if I have something squared equals 3, well, what squared equals 3? From units past, we know that the square root of 3, if I were to square that, the square and square root cancel, and I would be left with 3. So it has to be that 3 to the 1/2 is equivalent to the square root of 3. Right? And now that will follow this rule here. If P is an integer and R is a positive integer and B is a positive, and I'm just going to put the sign for the real numbers. So B is a positive real number. Then if I have B raised to the P over R power, that is equivalent to the rth root of B all raised to the P power. Okay? This is a big deal. So anytime I have an exponent that is raised to some fractional power, I can convert that over to a radical by just making whatever the denominator of this fraction is, that's the index of the radical, and whatever the numerator is ends up being what I'm raising that radical to. Right? So now, 3 to the 5 halves. If I were to simplify this, 3 to the 5 halves. 5 halves is 1/2 times 5. So what I just did is I broke this apart, 3 to the 5 halves. If I had 3 to the 1/2 raised to the 5th, if I multiply those exponents, that would give me 5 halves here. So this is equivalent. What I'm able to now do from before, if we come up here, we said that 3 to the 1/2 was the square root of 3. Well, here I have 3 to the 1/2. So that is the square root of 3 again, and then I have to the 5th power. Okay? So instead of having to break it all the way down to 3 to the 1/2 and realizing that that's the square root of 3, I can immediately go from exponential form to radical form just by this fact up here. Okay? So 3 to the 5 halves, that's going to be whatever the denominator is. It's the index here, so it's the square root of that base all raised to whatever the numerator power is. Now you can write it like that, or you can make it the square root of 3, and that numerator, that 5, can go inside the radical also. Both of these technically are the same answer. Okay? All right. So when we are simplifying, all rules of exponents and radicals apply, all of them. So if I want to go through and evaluate and simplify what I have here, notice if I'm multiplying just as radicals, I wouldn't be able to multiply these two expressions together because my indexes aren't the same. I have the 12th root of 8 and the 4th root of 8. In order for me to multiply, the indexes must be the same. So rather than using radicals, what I'm going to do is convert this over to an exponent problem, simplify using laws of exponents, and then rewrite my answer as a radical if need be. So I'm going to do that right here. Ready? So the 12th root of 8, that's the same as 8 to the 1/12. The 4th root of 8 is 8 to the 1/4. Okay? Now, what I'm going to do at this point, if you remember all the way back up here, when I wanted you to recognize these powers here, once you change something over to exponential form, you then want to look at the bases and see if you can break those bases down any further. 8 is 2 to the 3rd power. And the same thing over here. Now, notice I'm raising a power to a power. I can multiply those exponents. This becomes 2 to the 3/12 times 2 to the 3/4. And then 3/12 simplifies to 1/4. So now I have 2 to the 1/4 times 2 to the 3/4. And now all I'm simply doing, I'm multiplying like bases, so I can just add my exponents, which will give me 2 to the 1/4 plus 3/4, which is just 2 to the first power, which is just 2. So that whole thing simplified to just 2. Now I'm going to go a little bit faster here, so I'm going to do them all, and then you can rewind back and watch again if I go too fast. But for time purposes, I want to get through this. Here, this is going to be 625 to the 1/3 times 625 to the 1/6. 625 is 5 to the 4th to the 1/3 times 5 to the 4th to the 1/6. Multiply those exponents, gives me 5 to the 4/3 times 5 to the 4/6, which is 5 to the 4/3 times 5 to the 2/3. Once again, add my exponents. That's going to give me 5 to the 6/3, which is 5 squared, which is 25. Number 3. Same thing here. Now, I'm raising to a negative exponent. So remember, laws of exponents, if I have a fraction raised to a negative exponent, I can flip that fraction and make it a positive exponent. 81 is on that powers to recognize. That's 3 to the 4th power raised to the 3/4. Multiply exponents is going to give me 3 to the 3rd power, which is 27. Okay? Now, same thing here. I'm going to flip this, make this negative 125 over 8 to the positive 4/3. This is going to be negative 5 to the 3rd over 2 to the 3rd, the 4/3. Distribute those powers, and the 4s are going to cancel. So that's going to give me negative 5 to the 4th power over 2 to the 4th power, which is 625 over 16. Now, when I have big expressions, I'm going to do the same exact thing, but all I'm going to do is break them down separately. So here, if I have the 4th root of this whole expression, make it 16 to the 1/4 times x to the 11th to the 1/4 times y to the negative 4th to the 1/4. 16 is 2 to the 4th to the 1/4 times x to the 11/4 times y to the negative 1st. This gives me just 2. Now this is improper, 11/4. So notice that I have 2 full x's in here that I can take out. So I'll have x squared. I think of it like I'm going to write up here, x to the 11/4. That's x to the 8/4 times x to the 3/4. So I can take 2 full x's out of here that I have here next to this 2. But then I'm left with x to the 3/4. Y to the negative 1st, that's going to just move down to my denominator like this. And then notice x to the 3/4. If I convert that back to a radical, my denominator is the index, so it's going to be the 4th root of x to the numerator power, the 4th root of x cubed. And that would be my final answer here. We'll have time for one more here. The square root of x, that's x to the 1/2 times, this is going to be x to the 2/3 if I convert that over. Now, in order for me to multiply like bases, I need to add exponents. Well, I'm going to need a common denominator here. That's going to give me x to the 3/6 times x to the 4/6. Then add them is going to give me x to the 7/6 power. And again, that'll be x to the 6/6 times x to the 1/6. That'll be 1 full x right here. And then I have x to the 1/6 left over, which when I convert that back over, that's the 6th root of x to the 1st power. That will be my answer. Now I'm going to write what the answers are to number 3 and number 4 in your notes file, but for time purposes, I'm going to want you to go through and try those on your own. okay? And then we'll go through them together during our office hours. All right? All right, good luck, everybody.